as mobile sensing platforms that would be sent out in the world by a centralized mapping and planning system to reconstruct properties of this environment. So then using this information, a human operator could send in the team of commandos to go to the bank building and liberate the hostages. So that means this was very much a core concept, the mapping and planning stage, plus the presentation of this world model we're constructing in a virtual reality environment, so that the human operator could make fly-throughs and look at different perspectives, also understand under what conditions, for instance, the commandos would be hidden from view, on what conditions they would not, what distances you are from mines, objects, trees, and so on. All right? So, in some sense, this is also a statement on our side of where we see the field is going. It's not that all the problems at the robotic end are solved, but we can see we're getting close to solving them. Like in our case, we used, I think, a very good flying platform from Ascending Technologies, like the previous group, the German group, they were called there. I think it's an excellent platform to work with. So these are problems that now start to become solved, right? And I think the really hard challenges, in addition to many others, of course, are now very much in this question of how we're going to use this technology. And that's the one where we try to make some statements. So the planning model is essentially a statistical approach where you say, look, I'm sampling from a different set of mobile sensors in the world, which can be chemical, they can be distal, like collision sensors, they can be or they can be distal, like vision, like cameras, or proximal, like collisions. And each of these makes probabilistic statements about the world. Right? So then the next problem is, how do I optimally integrate this information and then subsequently transform that into something that I can call a world model. So we follow statistical approaches to do that. So here you see some results in our lab, where we use small mobile robots in large environments to perform reconstruction, where we get very good reconstruction results. And here in the planning stage, the whole concept is to say, look, if I sampled my world, if I know what's available at different positions in space, I now want to assign a value to every position, a cost, let's say, that expresses what the price is I have to pay when I'm going to enter this location. For if you suffer a collision somewhere, that would be a high cost. Right? So now your planner can start to optimize in this cost surface. So that's what we put together and also field it. Another aspect we introduced was a chemical sensor. This is a thin metal oxide sensor, a 6-grid array developed by Alphamos. It's a company in France that is specialized in chemical sensing, artificial noses, artificial tongues. So this is the device that they built, which we have packaged on a small board to make it also practical to fly around on an MAV, for instance. And the key concept of this sensor technology is that you have a broadly tuned sensor. You have a surface with which many volatiles can bind, which means you can potentially pick up responses to many sources, many types of chemicals. However, you have now a classification problem, right? Because now you have to interpret a very broad response profile with respect to the specific volatile you're interested in. But fortunately, this is also the strategy that's very much used in nature. And that's then again, from a scientific perspective, interesting. So if you want to build an artificial insect, or I believe if you want to be successful in real-world applications with olfaction, it's these kinds of broadly tuned sensors we want to look at. So here you see the responses in a wind tunnel test we do in the laboratory. Every circle here is a measurement point. These are the responses of the single sensors. Remember, there are 6 sensors in each package to ethanol. And it also illustrates the broad tuning, right? These guys are not all doing the same thing. It gives you very broad, dynamical response with lots of issues like drift, hysteresis, and so on. But you can use this to rather reliably reconstruct the plume dynamics, right? The structure of a plume. Because keep in mind, chemical sensing has some unique features, which is it occurs in a plume. The plumes are turbulent. It's not just gradient following. There are no gradients out there for chemical sensing systems like insects or ourselves. Here we do an outdoor experiment on a 40 by 80 field with a UAV, where we reconstruct a plume generated by a single ethanol source here at this location. Okay, so we knew from these experiments that our sensor would work on volatiles like ethanol, but then there were some surprises. Okay, in the meantime, we're doing a lot of work in mixed reality systems, so we exploited that to then map the world model we're constructing in real time to a virtual reality representation. It meant as soon as the mapping stage of our model, of our system, identified a surface, an object, a mine, it was automatically mapped into this virtual reality representation. Right? So the planner could see how the world would grow in real time as the robots would be going around. So these are the key components that we put together. So we ended up doing the demonstration because our flying platform was outside of the envelope. I tried to convince the jury that when the rotors turn, they bend, so then we're inside the envelope of the competition, but they didn't buy that. So in our demo, we showed the following components. It was yesterday afternoon. We used our MAV, human piloted, to do global surveying of the environment, identify coarse features in the environment, which we then used to define regions of interest, where then by the planner, the robot, the UGV, would be sent into to extract detailed profiles of obstacles and possibly mines. Right? So this is the strategy we fielded. We also showed was functioning. And we also successfully then showed that we could extract profiles of obstacles. We could insert them in the world model, update the planning, put them in the VR representation. And also we succeeded in identifying and reconstructing the plume in this environment, the chemical plume that we were sensitive to. However, so what worked is the distal proximal sensing, a mapping and planning, a virtual reality representation, and the chemical sensing. However, in this case, it was with Cheers 42% local whiskey. It's 100 rupees if you're interested, but I don't think it's drinkable. But the chemo sensors like it very much. So, in some sense, these core components of our systems work really well. But of course, life is also filled with problems. We brought, yes, I'm on track. Last slide. We brought 3 UGVs. We sacrificed 2. One died mechanically, gearboxes essentially. Second one was cannibalized for spare parts. So the third one was in the end fielded. So this is definitely an issue we have to deal with. We're now working with a company called RoboSoft to solve that. The MAV autonomy, I think the platform is great. But unfortunately, we were not able to buy from the company we were working with the autonomous version of this system. So this would help us a lot for the planning stage. But we know this is available, so this can be done very quickly. Communications, as with other teams, definitely a problem, lots of interference, something to improve. Chemical sensing, well, as you saw, we could reconstruct the plume of the ethanol, but the TNT that we were asked to detect not that long ago actually, turns out to only give a deflection in the sensor response of 1% of the variance in the baseline. So that means this is a hopeless detection task, right? With this sensor for TNT. So it illustrates again, mobile chemosensing technologies for substances like TNTs are still a bit in the future. And then last point, right? The very last issue we will then pursue more as a basic science exercise is the whole issue of robot team strategy that we will show to you next time around. Thank you very much.